From today, we will start the unit of applications of differential calculus. We need to look at the applications of differentiation in three different areas. The first one is the application of differentiation in physics, which is called kinematics here. The second application of differentiation is called the rates of change in different real-life areas. The last application we will learn is called optimization. We need to look at how we can apply differential calculus to optimize the revenue, the cost, the surface area, the volume, etc. Each of students will learn one more application of differential calculus, which is called related rates. So we will learn every single application one by one. The first application is kinematics. We need to look at the motion problems of displacement, velocity, and acceleration. The first task you need to do in this lesson is to read the opening problem on page 414 for SL students. HL students, you can find the opening problem on page 592 in your textbook. So let's look at the SL students textbook. This is the opening problem. So Michael rides up on the hill and down the other side to his friend's house. The dots on the graph show Michael's position at various times t. So this one shows where Michael is at different times. This is also called the motion diagram. This equation is the relationship between the displacement and time on a restricted domain for the time. Of course, the curve between the displacement and the time can be a curve, but the motion diagram is a straight line. So we only research the motion on a straight line, but the displacement versus the time graph can be a curve, can be a polynomial function, or sinusoidal functions, or different types of the functions. So I also hope right now you can think about those 5 questions. Think about how I can apply my existing knowledge to answer those questions. Of course, after you finished this lesson 8, you should have no trouble in answering those questions. Let's look at the difference between distance and speed and displacement and velocity. Consider the movement of a person riding his bicycle if we don't know the direction the person is traveling. So we talk simply about the distance he has traveled and his speed. That suggests the distance and the speed don't involve the directions. If we know the direction the person is traveling, especially his motion is in a straight line, of course, that's what we just talked about, we can therefore talk about displacement and velocity. Therefore, the displacement and the velocity should involve the directions. Let's look at the displacement versus the time. Displacement. Suppose an object P moves along a straight line so that its position S from an origin O is given as a function of time t. We write S equals S of t, where t must be greater than or equal to 0. We usually don't talk about negative time, so we always count the time forward. T should have this one as the domain in the function between the displacement and the time. S of t is the notation for the displacement function, and for any value of t, it gives the displacement from O. S of t, displacement, involves the direction. Therefore, this is a vector quantity. Some of the students have already learned this one in physics. We should have this one after the vector units. If we learn the vector units first, you know displacement is a vector, which means you do not only have the quantity, but also have the direction. Its magnitude is the distance from O. How far the object P is away from the origin O. And its sign indicates the direction from O. Usually, the right side is the positive direction, just like the number line. So this one is the positive direction. This one is the negative direction. So the sign of the displacement function versus time. So when s of t is greater than 0, it's positive sign. This P should be on the right side of the origin. If s of t equals 0, this object P is located at the origin O. If s of t is negative, less than 0, so this object P is located to the left of the origin O. Section 4, motion graphs. If we are given the function between the displacement and the time, how can we find the displacement at different times? And thereby we can draw the motion graph on the number line. So let's look at this example. What we need to do is find where the object P is at each time moment, like t equals 0, t equals 1, t equals 2, t equals 3, t equals 4, etc. So s of 0 means in this function, t equals 0. Let's sub 0 in for t. So 0 squared plus 2 times 0 minus 3 should be negative 3 centimeters. So when t equals 0, the moving object is at the left side of the origin O, and it's 3 centimeters away from the O on the left side. What's the meaning of s of 1? So when t equals 1, where is the moving object P? T equals 1, let's replace t with 1. So it should be 1 squared plus 2 times 1 minus 3. It equals 0. So when t equals 1, the moving object moves here. So from t equals 0, that's where the moving object is. To t equals 1, that's where the moving object is. So t equals 0 to t equals 1, the moving object moves from this one to this one. Okay, the same. Let's find s of 2. S of 2 should be 4 plus 4 minus 3, which is 5 centimeters. Don't forget about the unit. We should put on centimeters for 0 as well. So 5 centimeters is a positive value. That means when t equals 2, the moving object should be on the right side of the origin O. And at that time, the moving object is 5 centimeters away from the origin. So from t equals 1 to t equals 2, that means the moving object P goes this way, from t equals 1 to t equals 2. Then s of 3 should be 9 plus 6 minus 3, which is 12. So t equals 3, the moving object should be at 12 centimeters away from the origin on the right side. That means from t equals 2 to t equals 3, the P is moving this way, from this one to this one, from 5 centimeters to 12 centimeters on the right side. Then let's look at s of 4. So s of 4 should be 16 plus 8 minus 3, 21. So at t equals 4, the moving object P is 21 centimeters away from the origin and on the right side of the origin. So from t equals 3 to t equals 4, that means the moving object is going this way. Look at the entire graph from t equals 0, where the moving object begins, all the way to where the moving object ends. You will see the moving object P is moving towards the right continuously. But not all the motion diagrams will moving with one direction. Some of the motion diagram will be moving right, then moving left, then switch back to the right direction, then move left again, then move back to the right, it could happen with different types of the displacement versus the time function. Section 5, velocity. Please note that you need to develop clear understanding about the difference between the average velocity and the instantaneous velocity. What is the average velocity? The average velocity of an object moving in a straight line in the time interval from t1 to t2 is the ratio of the changing displacement to the changing time. Average velocity equals the changing displacement over the changing time. So s of t2 minus s of t1 over t2 minus t1. You don't have to use t1, t2 to show these two different locations. Just like what we did in chapter 14 when we introduced the first principles, we also can say this one is s of t and this one is s of t plus h. They do have a time gap, or you can see the change in time is h. So you can also say s of t plus h minus s of t over h. Anyways, what is the average velocity? The average velocity is the gradient or the slope of this straight line. Therefore, the average velocity is the gradient of a chord through 2 points. So t1 as t1, t2 as t2. You also can say t was s of t, t plus h was s of t plus h. What is the instantaneous velocity? When the displacement versus the time graph is a curve shape. So the instantaneous velocity is the velocity at an instant, at a time t equals a, for example. So that means I'm looking for the gradient of this tangent line to the function s of t at a point t equals a. Therefore, the velocity function, which is also called the instantaneous velocity, is the first derivative of the displacement function, which is the limit of this slope of the chord. So the slope of the chord with the limit when h approaches 0, it becomes the slope of the tangent line to the curve at a particular time. So on a graph of s of t against time t, the instantaneous velocity at a particular time is the gradient of the tangent to the graph at that point. Likewise, let's look at acceleration right now in section 6. If an object moves in a straight line with velocity function v of t, then its average acceleration for the time interval from t1 to t2 is the ratio of the change in velocity to the change in time. So the average acceleration should be the gradient or the slope of a chord between 2 points on the velocity function. So this is the change in velocity over the change in time. What is instantaneous acceleration? Instantaneous acceleration means you need to look for the gradient or the slope of the tangent line to the velocity function at a particular time t. So therefore, the instantaneous acceleration should be the limit of the gradient of this chord when h approaches 0. And when you put the limit symbol when h approaches 0 for this slope of the chord, this one becomes the first derivative of the velocity function based on the first principles. Therefore, what is the instantaneous acceleration? The instantaneous acceleration is the first derivative of the velocity function. Section 7, units. The common units we usually use for the velocity and acceleration could be meter per second, kilometers per hour. So they are the common units we used for velocity, including average velocity, instantaneous velocity. Meter per second squared, that's a common unit we usually used for the average acceleration and the instantaneous acceleration. Example 1. A particle P moves in a straight line with a displacement function of s of t equals 5 minus 2t squared centimeters, where t is greater than or equal to 0, t in seconds. A. Find the average velocity from t equals 2 to t equals 5 seconds. B. Find the average velocity from t equals 2 to t equals 2 plus h seconds. C. Find the value of limit s of 2 plus h minus s of 2 over h when h approaches 0, and state the meaning of this value. D. Interpret limit s of t plus h minus s of t over h when h approaches 0. So based on what we just introduced in this lesson before this example and what we learned from chapter 14 or chapter 17 for HL students, right? So you should know average velocity is the gradient or the slope of a chord between 2 points on this function graph. So it should be the change in the displacement over the change in time. So s of 5, you plug in to find this value. So this one should be negative 45. Minus s of t. Plug 2 into this s of t function for t, so we can find a negative 3. Divided by 3. So the average velocity is negative 14 centimeters per second. Let's look at the average velocity from t equals 2 to t equals 2 plus h. So it's still the same as A. Average velocity is always the gradient of a chord between 2 points on the graph of s of t. So it should be the change in the displacement over the change in time. So the change in displacement should be 5 minus 2 times 2 plus h squared, then close the square brackets, minus 5 minus 2t squared. This t should be 2. So let's replace this t with 2 and squared. Over the bottom is just h. So positive 2, negative 2, got to cancel out. So right now what you need to do is just expand the brackets in the numerator and simplify it. So after you open the brackets, you can have 5 minus 8 minus 8h minus 2h squared plus 3 over h. So it should be negative 8h minus 2h squared after you combine the like terms over h. We can reduce the fraction to the lowest term. So we take out 1h in the numerator divided by h. So we should have negative 8 minus 2h centimeter per second. So that's the average velocity in terms of h. So how can we find the value of this limit in B when h approaches 0? So that means I'm just looking for the limit of negative 8 minus 2h when h approaches 0. So we can use sub-in method. H equals 0, let's sub-in. It should be negative 8 centimeters per second. What does this value represent? So this negative 8 centimeters per second should represent the instantaneous velocity of the moving object, of the particle here, at time t equals 2 seconds. Later on, you don't have to go through this first principle at a particular point to find an instantaneous velocity at a time t equals 2 seconds. You can just work on as the velocity function equals the first derivative of the displacement function. The first derivative of the displacement function should be negative 4t. When t equals 2, don't you think the instantaneous velocity is really negative 8 centimeters per second? Okay, let's look at D. So limit s of t plus h minus s of t over h when h approaches 0. What does this one represent? This one represents the velocity function. This velocity function is the first derivative of the displacement function based on the first principles. Try to do the homework questions to help you practice your understanding on the average velocity, instantaneous velocity, average acceleration, and instantaneous acceleration further. So this is the end of this lesson.